Welcome to Future Frontiers. Today, we're looking up, way up, beyond our solar system, to the stars. Alpha Centauri, our closest stellar neighbor, is over 4 light-years away. With current tech, like the Voyager probes, that's a journey of tens of thousands of years. To reach the stars within a human lifetime, we need to hit relativistic speeds, a significant fraction of the speed of light. And that's where beam propulsion comes in. The core idea is simple. Instead of lugging massive amounts of fuel, as current rockets do, we transmit energy to the spacecraft from an external source. This beam, whether light or particles, pushes the spacecraft, accelerating it to incredible speeds. One popular concept is laser propulsion. Imagine an intense laser beam pushing a large, reflective light sail. Projects like Breakthrough Starshot are exploring this, aiming to send tiny nanocrafts to 20% the speed of light. But it's tough. You need gigawatt or terawatt lasers, and keeping that beam focused over millions of kilometers is a huge challenge. Plus, the laser is only effective for a short acceleration burst. Then there's particle beam propulsion. Relativistic electron beams are particularly interesting. Electrons are light, easier to accelerate near light speed. A neat trick called the relativistic pinch effect helps keep the beam focused over much longer distances. Think hundreds or even 1,000 astronomical units. This means weeks or months of continuous thrust, possibly pushing a 1,000-kilogram spacecraft to 10% light speed, reaching Alpha Centauri in about 40 years. The spacecraft would use a magnetic field, a mag sail, to reflect these particles. We could also use neutral particle beams to avoid beam expansion, or even streams of tiny hypervelocity pellets impacting a pusher plate. Some even propose combining laser and particle beams, creating a self-reinforcing soliton wave that resists spreading, guiding both beams over incredible distances. But the engineering challenges are, frankly, astronomical. First, the power. We're talking unprecedented energy levels, maybe needing dedicated space-based solar power plants near the sun. Keeping beams coherent and focused across interstellar space is a monumental task. Building the emitters, whether giant laser arrays or particle accelerators, is a colossal undertaking. The spacecraft itself, especially a light sail, needs to be incredibly thin, lightweight, yet super strong and heat-resistant. Imagine materials like nanoscopically thin aluminum oxide surviving intense laser heat. Maintaining sail shape and stability is critical. Perhaps they'd billow like parachutes. And then there's pointing the beam. Imagine hitting a small sail billions of kilometers away with pinpoint accuracy. Autonomous systems are key, as real-time adjustments from Earth are impossible due to communication delays. Speaking of communication, how do we get data back from a probe light-years away? Maybe the sail itself becomes an antenna. And once we get there, how do we slow down? That's another massive hurdle. Using a reverse beam from the destination is unlikely without infrastructure already there. So this isn't happening tomorrow. Beam propulsion for interstellar travel is a multi-generational quest. Initiatives like Breakthrough Starshot are tackling the fundamental science and engineering. We're seeing progress in materials science for sails, in understanding beam physics, and using AI for design. Future breakthroughs in energy, materials like metamaterials, and autonomous systems will be vital. It requires global collaboration. The journey to the stars using beam propulsion is daunting, but it's a pursuit that drives innovation and expands our vision of what humanity can achieve.